Well, hello everyone, yet again. Today I am going to be discussing network basics for people who don't do networking. So this is really going to be for people that don't really care about networking, but need to know at least a basic level of network terminology, functionality, and devices and layouts and that kind of stuff. So we're going to dive right in. So the topics I'm going to discuss are the different types of networking models. So there's the TCP/IP and the OSI model. We're going to dig into a couple of different layers. I'm not going to actually dig into the models exactly as they are, and you'll kind of see here in a minute what I'm talking about. I'm going to briefly mention some devices and then also some network layouts just to kind of help you visualize what I'm talking about. So the different networking models, the OSI model has 7 layers, the TCP/IP model has 4 layers. They're really used to help make logical sense of how stuff flows through there, and they don't do a great job of it. You'll kind of see how they are a little convoluted at times. But even for like certain protocols, they don't quite fit into the same layer that you would expect compared to another protocol. But I just wanted to, it helps at least conceptualize it. And so when you're talking with somebody about networking, you can at least say, oh, well, this layer or this layer, and kind of level set. One thing to note is when you're looking at the network models, the information is actually passed down. So when you're interacting with it, you're interacting with an application. And so that's happening at the top level. And so as it goes down, it gets encapsulated into different layers. So more information is added onto it. So you start with just like your typical hello world. And then that gets encapsulated into application data. And then that gets added on. This might help a little bit. So here's your networking models. So you have your TCP/IP over on the left side, which you can see only has 4 layers. And then you have the OSI model on the right, which has 7. They do the same thing. It's just a different way of looking at how it works. And so I'm going to kind of do a hybrid today, where I'm taking layers 1 and 2 of the OSI model, so the physical and the data link. Then you have the network and then the transport. And I'm going to include the transport in the application settings, or in the application layer. So it was still 4, but it's going to be a little bit different than the TCP/IP model. So exactly what I just was saying. So we're going to have our layer 1 physical layer, which is just going to be your cabling and your electrical signal, the 1s and 0s, which I'm going to throw out the word bit here. That's going to come up here in a second. Then we have our layer 2, we have our data link. That's really your local area networks, a lot of your home networks. That's really all you kind of have up until you get to your home router, and then it goes out and then it becomes the internet. So then you have your layer 3, which is the internet layer, and you have your IP addresses and your routers at that level. And then you have layer 4 and above, which includes the application and transport and TCP, UDP, sockets, ports, application data, firewall, IPS, WAF, a whole bunch of stuff. We're not going to get into a whole lot there, but it is important to kind of call it out because that's where a lot of stuff that your day-to-day really kind of exists. So layer 1, just continuing along, refers to the physical aspects of the network. It's the cables, it's the signaling. So if you're dealing with, excuse me, just like your standard Ethernet cable, it's electric for the signaling type. If you're dealing with wireless, it's radio frequency. And if it's optical, or fiber, I should say, then it's optical. But I'm not going to really go into a whole lot of that because it gets complex and you really don't need to worry about it too much. But the important aspect of this is the data unit, which is the bit. So a bit is a 1 or a 0. And carrying right along, we're going into our network math. So a bit is a binary unit. So base 2, 1 and 0, you're able to encapsulate that into actual data. So it's not just a 1 or a 0. You can string it together and actually create larger quantities of data. I've kind of listed out some common, semi-common. Octal is not super common, but you might see it in the CTF on a challenge or two. Then you have decimal, and then you have hexadecimal. All of these are just ways to interpret numerical values. So a bit is 1 unit of binary. So it's 0 or 1. And I'll kind of in a couple of I think it's actually the next slide is for binary. But so anyways, you have your bit, you have a nibble, then you have a byte, which also can be described as an octet. After that, you get into your word, which is 16 bits, and then you have double words, which is 32, and then you have quad words, which is we'll leave it without that. Developers probably know what I'm talking about, but not even network engineers don't really deal with that too much. So this is where binary, like, it's going to be a very brief explanation of binary here. But each place going from your least significant digit, which is over on the right, to the most significant digit on the left, has value. So you start with 2 to the power of 0, which is just 1. Then you have 2 to the power of 1, which is 2, and then 2 to the power of 2, 4, 2 to the power of 3, 8, so on and so forth. So every time you put a 0 or a 1 there, you're turning on that bit or that value, and then you add all those together. So in this scenario, all the bits are turned on, so you have a total of 8 bits that are all in a byte, for a total of 255 binary value. Then you also have hex, which I'm covering specifically for the aspect of MAC addresses and IP version 6, which we're not really going to talk about, but it's out there, and you're going to see it in the CTF. So hex ranges from 0 through 9, then A to F, so A being 10, B 11, C, so on and so forth. The hex values that you would place into a byte are just 2 hex letters. So you have 16 to the base, or to the power of 0, and 16 to the power of 1. And then you're multiplying 1 times anywhere between 0 and 15 times for the first character on the least significant digit. And then you have 16 to the 1 power, which is 16. So 16 times anywhere between 0 and 15. So in this scenario, I'm doing FF, which would be the same as the last one, for a total of 255, because everything's turned on. So 255. And again, this is just showing that thing earlier. So we have our nibble, we have our byte, and there's that word I was talking about. And you'll see that 0x is is how you can display a hexadecimal number. So you'll see 0x for hex, you'll see 0 O, lowercase o, for octal, and then if you see zeros and ones, you have binary. All right, so moving on, we have layer 2. This is getting back into the actual networking portion. So simple network communication. So this is your home network, your local area network. Your typical device that is on the layer 2 is your switch. It has some intelligence. It's using MAC addresses for addresses. So every device has a MAC address associated with it. And the data unit that it is using to actually pass that data is a frame. So talking a little bit about MAC addresses, every MAC address, it's a 6-byte hexadecimal address that has been physically assigned by the hardware vendor. It is possible to change it, but not normally. For the most part, every MAC is unique. There are scenarios, both malicious and just because you need to, where you can change that MAC address. But for the most part, it doesn't change. And the first 3 bytes of that, so this 1C, 1B, 0D, in my example, is the hardware vendor ID. So you can kind of see the 1C, 1B, 0D is gigabyte, which I have a gigabyte motherboard on my desktop, so that is what is there. Next, we have layer 3, which allows for internet. So it's internetworking of LANs. So you're taking those local area networks and you're adding them together. So you're taking that MAC address based network and you're expanding it. And for this discussion, since we're keeping it very low level, we're just assuming it's an IP network, not anything crazy. So you have your IP address and your subnet mask. Some of you may not realize what the subnet mask does. We're going to talk about that in a little bit as well. And the data unit for this is a packet. So your IP address for version 4 is a 4-byte address separated by periods. So a lot of you are going to be very familiar with the 192.168.1 or .100. I mean, it depends on what your router at home really auto assigns. You can manually assign an IP address. You can have it auto assign. Typically at your home network in most places, it's just auto assigned unless you start getting into the servers or stuff that you specifically need to access via the IP, and then you want to make sure that you have that statically assigned or manually assigned. This is a virtual address, so it's not something, obviously, if you're able to change it, it's not something that has to stay the same. It's just data that gets assigned to it. And so you also have a subnet mask that correlates with that IP address. And that subnet mask will correlate to what is the network portion of the address. So as we were just talking about the local area network, you have a host portion of your IP address, and then you have your network portion. So in this case, when your subnet mask has the bits turned on, so all of these bits here are turned on, so the first 3 octets of this IP address are actually the network address. So sometimes you'll get asked by the network team or your ISP, like, hey, what's the network address? And so that would be the network address there. And then your host address is the full IP, but really it's the last octet or the last portion that's not covered underneath the subnet mask. And so the size of the subnet is going to correlate to the size of the layer 2 network. So depending on how many switches you have put together and how many devices you need to have on your local network, you're going to have that size of a subnet. And what I mean by that is, as we were just talking about, this first portion with the bits turned on, that's the network portion. So you can't use the 192.168.1 addresses to assign. You can't change those. Those are specifically for the network that you're on. This last portion can change. So that means that of the last 8 bits, those can be in whatever order you need them to be, but those are going to be the only options you have to assign to devices. So technically, it's a maximum of 254 devices that you can have on that subnet. So that's something to note. If you're not planning a local area network, you don't really need to worry about that. That's all part of the architecture side. But that does let you understand kind of if you see a larger, so another way to look at your subnet mask is CIDR notation, which is the slash notation. So you'll see like 192.168.1.0/24. And what that means is 24 bits of your subnet mask are turned on for the subnet mask, or the host address. So these two are interchangeable for the subnet mask. So as a system starts to prepare for a network request, it's going to take that data down from the application and it starts encapsulating it. And so the first thing it does is, for our portion of this, is it adds the layer 3 header. So it adds the IP headers, and then after that, it will add the layer 2 headers. But there's certain logic that it needs to actually consider before it does those portions of it. So the IP headers get added, and that's really whatever your application wanted it to be. So if you're saying, hey, I want to connect out to google.com, it's going to use DNS to figure out what the source address or the destination address is for google.com, and it's going to say, okay, well, my address is this, the destination address is this, and it's going to fill in these two portions of this header. There's a lot of stuff in here, and don't worry about it. It's a pain. So once the system realizes, hey, this is where I'm going to be sending my traffic, it's going to look at its route table to determine what interface it should send that traffic. And so that's where it's going to figure out that source, the source IP. So you can see your route table on pretty much any system. Route print on Windows, since that's what I'm on, you're able to type that in and you'll get an output similar to this. There's actually a lot more, but I just cut it down because I have a bunch of VMs and stuff like that. But you'll see, like, for the 192.168.1.0 network, it's going to use my local IP that is directly connected to that network. And if it doesn't have a network specified for it, it's going to use the default route, which is quad 0. So 00000, netmask 00000. So this is anything matches this, and that's where it's going to send it. So it's going to go to that interface, and it's going to use the default gateway that I have specified. So the next portion is after it's determined, hey, okay, here's my layer 3 information. You saw that it's going to use that default gateway. So it's going to say, okay, I need to go out onto the network. First thing it's going to do is it's going to take the source MAC address for whatever interface it's going out. So it's going to take the MAC address of the 154 IP address. And then the next portion is it says, where am I sending this? Because a MAC address has to be translated to a IP address in order for it to know where to go. So that's where the MAC table comes into play. So the MAC table is just a list of all the MAC addresses and their associated IP address. So here's an output from my computer. You'll see that my default gateway has a physical address of this. So you can figure out that that's, I'm assuming this first part is ASUS because that's the brand router I have. But you can see there's a bunch of different other options in here. And each device on the network maintains its own MAC table, and they build it using ARP, or Address Resolution Protocol. I'm not going to go too much into that because it's another big topic, but it basically, when you connect to the network, it broadcasts and says, here I am, here's my MAC address, and everybody will document it and hold it. And if for some reason somebody connects and they don't know where another device on the network, so if they're on the same subnet, they can send the traffic directly to that device. So they'll send out an ARP request saying, hey, who has this IP? And somebody will reply, I have it. And so then they'll send it to them. So on Windows, you can use ARP-A, similar to the route print, to get your information, just like I did below. And so once it has that source and the destination MAC address, it adds that information to the layer 2 frame headers. So you'll see source, destination, ether type, which we're not going to cover at this point, and then checksum for any errors. The MAC addresses will change at the layer 3 network. So on the layer 2 network, it's all one network. So the source and the destination, it will say, hey, here you go. And the switches will deliver the traffic to the destination if it's on the network. In the case of using the default gateway, so it's not on the network, so you're going to a layer 3 device, the source and the destination get updated. So the router will then update the destination to be wherever it is in its routing table, and it will update the source address with the interface, the MAC address of its interface of wherever it's sending that out. The IP address and the IP header stays the same though, with the exception of it being manipulated by network address translation, which we're going to talk right now about, because RFC 1918. So RFC 1918 is a declaration of private IPs and public IPs. So you have your private IPs that are used for your local networks. They are not routable over the public internet. So if you were directly connected to the internet and you didn't have a local area network and you tried to reach an IP address in any one of these 3 network areas, it's not going to work. And that's specifically because those are reserved for corporations, enterprises, local home networks. Those are free reign. And it's because if you have those defined on the internet and you're using those inside your network, if you were to try to reach a internet site that had that address and it was internal to your network's going to prefer the one that's local to it, and you won't be able to route to it. And then your public IP addresses are just those that are out on the internet. So you'll get those from your ISP, and that's how you get traffic sent back to you when you're browsing the internet, or in the case of a business, that's how you get people to access your websites. So network address translation there's a couple different types. So one-to-one network address translation is basically providing a dedicated IP for an internal device. So you can say, all right, here's my public IP. I want to, or one of my public IPs, if you have a range of them, you could say, I want this public IP to be dedicated to my web server / email / if you host multiple things on the same device, you can do it like that. There's a better way to do it, especially when you have all those services spread out over a bunch of different hosts, and that's a port address translation. But first, a many-to-one address translation is typically used for outbound. So at your house, if you were to go to like ipchicken.com, or if you're on the command line, you can use curl ifconfig.me. It'll show your public IP address. And so if you do like a IP config on your local workstation, you're going to have a 192.168 or whatever address that's internal. It's a private IP. But when you go out in your browse, your router, your home router, will actually be doing a many-to-one network address translation. So port address translation is very similar to that, but it is used the opposite way. So you basically have one IP assigned to your edge device, your router, and you say, I want to have this port go to this internal device, or this port go to this internal device. And I have some diagrams of this in a second, but you might have also heard this as like port forward on your home router. So if you have like anybody that plays video games, sometimes they require you to port forward a certain address, or if like a Plex server or something like that, to allow the traffic to that port to get into your device and be able to access it from the internet. So here is an example of the network address translation. So this is a like a one-to-one network address translation. So the first one isn't really a network address translation, because typically the outside interface of your firewall would be assigned this IP. So you would have it assigned the 225.43.1, and then your internal interface over here would be assigned the 192.168.1.1. But then for everything else, you would have a network address translation configured on the firewall that says, hey, if 225.43.2 comes in, go ahead and translate it to 192.168.1.10, and that traffic would then look like it's coming to the web server. And then same for the other ones down below it. And then this is a port address translation table. So the first one, again, it doesn't really need to be there because that public IP is already on that device. But you could say, okay, if anything else comes into .1 on port 80, then I want you to translate it to 80 for the web server, or 25 for the email server, or 5060 for SIP going to the phone system. All right, so now we get into the convoluted portion. One second. So layer 4 is where the OS and the application layer start kind of merging together. You have TCP and UDP that are the main protocols that we're going to talk about. You also have ports and sockets, which are really the addressing, if you will, that we're going to deal with at this layer. So TCP and UDP are both going to be encapsulated inside layer 2, layer 3 headers. TCP is stateful, so you'll hear the term sign, SINAC, ACK, and that's really talking about the three-way handshake for TCP to establish that stateful connection, whereas UDP just will send it out, and if it gets there, great. If it doesn't, it gets dropped. TCP is good for slower, more applications that are okay with having a little bit slower of a connection. UDP is typically used on your streaming applications, so like voice, video games, possibly. I'm not quite sure what they're using, but it's, you don't care if it gets to the other side at, you'd care about it getting there, but you don't want it getting there out of order. Because what happens with TCP is if it gets sent and for some reason on the internet it gets dropped, it acknowledges those transmits. And if it's acknowledging it and it says, hey, I didn't get one, then your device is going to resend it. And so that delay, especially for like real-time media, that turns into call quality issues or choppy video. So that's why UDP is typically used. And then you have sockets. So sockets are typically specified after an IP address using a colon. So 192.168.1.1:80 or :443. You might see it specified as port 40 or port 80 or port 443, something like that. They both are saying the same thing. Typically, if you're going to a web address, you're going to do something like http://192.168.1.1.8443 for like a specific web server that's running on your router or something like that. But anyway, sockets are bound by applications to allow their network traffic. So they'll listen on that port, and when something connects to it, it's able to offer its application services over that port. And then also when you're initiating a connection, outbound, the application will typically, let's say you're connecting to a web server, it will typically just select a port in this what they call the ephemeral port range, and this is, it depends on what system you're on, but it can be really anywhere between like the 1025 and 65535. So huge range, but it's just, that's allowing, in case there's multiple people on that same system, it can have some session stability there. And so here's some well-known TCP ports. You're going to see some of these on the CTF. So you got FTP, SSH, SMTP, which is your email. You also have IMAP, POP3, but I didn't include those. HTTP for web, HTTPS, which is secure web, and then you have 445 for SMB, Samba file share. So now we're going to talk about some devices. Thanks for staying with me this long. So firewalls, these are network security devices. So they allow for access control lists to be used. You can base them off of the source or the destination IP address, or the source and destination port, if you want to use like an extended access list. They're typically just allow deny. It's really just to prevent known bad actors or restrict traffic to known good actors to a specific service. So in the US's case, a lot of the times you would block like traffic from Russia and China and North Korea and Iran, all the places that typically are trying to hack US companies. You would just block those, because why do they need to connect to any of your stuff unless you have a business case for it? And then you have your IPS, which can be on the firewall. A lot of the times it is separate now. They have virtual versions now. But anyways, it utilizes signatures to block malicious traffic. So it's kind of like an antivirus for your network traffic. And those signatures can be built either custom by an engineer, or they can be delivered from the vendor via subscriptions or downloaded and installed. But yeah, that's, IPSs are antivirus for the network, kind of. And a web application firewall is very similar to an IPS, but it is very specific for web-based applications. So it uses rules that can be configured to block malicious traffic to web applications. It's typically used to prevent known malicious actions. It also allows you to react quickly. So if you realize that there's some type of vulnerability in your application, but you can't patch it quick enough because you don't know the ramifications, you can deploy a rule to the WAF to block that. The danger there is it's all based off of, a lot of them are regex matches. So it's going to really depend on, is your rule able to cover all of the known malicious actions? And obviously you can put more and more rules in there, but depending on the applications and the different layers, you can, the malicious actor can really obfuscate their attack to different levels and bypass the WAF. So safe coding practice is still a must. So here is an example of a simple home network. I just kind of want to give a visualization of it. So here you have your layer 2 network. So really you got your printer, your desktop, your smartphone, all connected to a lot of times the router has a switch module built into it. So it's all layer 2. Each one of these would have a MAC address table. And if I wanted to talk from my desktop to my printer, I would be really talking at layer 2. Obviously layer 3 comes into play because that's how the applications go. But I would be able to direct that traffic over to the printer without the router having to make any routing decisions. And if I wanted to go out to the internet, that's where the routing table on the router would come into play. And then you have your work network. This is a very, very simplified one. This would be more of like a small business. Obviously, they only have 3 servers and 2 workstations, so pretty small. But your firewall could replace your router technically, performing routing decisions. So it would be the layer 3 termination point. And you'll see that this is a layer 2 network and this is a layer 2 network. So you have your server network that's 192.168.1.0/24. So you have that 254 available hosts on the network for your devices. And then you have your switch here that is facilitating that layer 2 communication. And then same thing down here, you got your 2.0/24. So if you were wanting to just print and it wasn't mapped to a server, you could just print directly to the printer without having to go through the firewall or through the switch. So if you were wanting to get to your internal web server from this network, you would have to go through your switch, and then you would go to your firewall, and then you would go to the web server. So you could have the firewall could have like an access list here, but more importantly, the change here is going to be you have here's your source MAC address, and it's going to say, oh, I need to get to the web server. In its ARP table, it's going to have the destination MAC address for the layer 2 being here, even though it's the IP address is saying, hey, 192.168.1.10 or whatever it is. The MAC address is going to be showing here. So then it's going to say, oh, okay, let me send it here. As soon as the firewall gets it, it's like, oh, it was destined for me on layer 2, but let me go ahead and go to layer 3. Oh, it wants 192.168.1.10. Okay, let me go ahead and let me re-encapsulate this in layer 2. So my source MAC address is now going to be this interface here. And then the destination MAC address is going to be for the web server. So I hope that kind of makes sense. And that's the presentation. So hopefully that makes a lot of sense. I mean, we covered a lot of stuff, and Cisco makes a lot of money off of their networking products and training and all that kind of stuff. There's hundreds and hundreds of pages of stuff on networking. So this was very, very brief. I hope this kind of helps you understand some of the topics without being mind-numbingly dull and without being too complex. Obviously, if you have any questions, feel free to reach out. But hopefully this will help you in your day-to-day job and in the CTF and in life in general. All right. Have a good one.